Okay. In case you want to say anything, make sure you drop it in the chat. We shall be in position to see it. Now, in the first question, we said we are synthesizing let me drop my number. Okay. So the first question that I gave, we are synthesizing ethanoic. This is ethanoic acid. Ethanoic acid from propanol. So when you look at this synthesis, the first thing you notice is that you realize that the number of carbon atoms, the number of those carbon atoms has actually reduced. So the number of the carbon atoms has reduced in number. So what comes to my mind is that I have to reduce on the number of carbon atoms. So the only way I can reduce, there are many ways of reducing the number of carbon atoms, but one appropriate way that we can use here is by creating a carboxylic acid. Then after we decarboxylate. So this one we can decarboxylate. That is one way we can reduce on the number of carbon atoms. Then there are those synthetic routes that require us to increase on the number of carbon atoms. I'm going to show you shortly after some time how those specific reactions that do that. Now here, I was actually intending to reduce on the number of carbon atoms because here we are having 3 carbon atoms. Here there are 3. Then here I'm having 2 carbon atoms. So the only way I could do that is that I could actually make a carboxylic acid. So from here, from an alcohol to a carboxylic acid, what do? I use an oxidizing agent. In this case, the oxidizing agent, the common oxidizing agent is manganate. Manganate, 7 potassium permanganate in the presence of an acid, and we heat, we form that carboxylic acid, that is propanoic acid. I can decarboxylate, in other words, to remove this whole carboxyl group. Removing that carboxyl group makes me end up with a compound ethane. So if I have ethane, what I can do, in other words, I now need to introduce the carboxyl part there. I can add the halogen atom there using, either you can use limited chlorine in the presence of UV light, or you can use this dibenzoyl peroxide. So I can form that. Then from here I can move to an alcohol. In other words, reacting that with sodium hydroxide, then I heat. Then after, I can oxidize the primary alcohol to form a carboxylic acid. Then the second part here, we're actually synthesizing. This was here 2-methyl. This compound is 2-methyl propane to all. So we are, no, 2-methyl propane, propane 2-ene, not all, because we are dealing with this one here is an alkene. Two-methyl prop. So what we are going to do is that I'm moving from this up to this compound. What I'm going to do is that you realize that this reaction is involving an increase in the number of carbon atoms. The number of carbon atoms are increasing. So one procedure that I can use to increase the number of carbon atoms is using a a Grignard's reagent. So I convert this into propanone. Then after I use a Grignard's reagent, and actually I make this intermediate, then I hydrolyze that to form this secondary alcohol. Then I use concentrated sulfuric acid. In other words, I dehydrogenate that to form for me this alkene. You guys can be taking screenshots there very fast. You can be taking screenshots on that work. I just wanted to show people the solutions to the numbers I gave because I promised people data in case they were able to, to do the work. But right now it looks like people never did the work. So I'm showing you the solutions. Screenshot that so that I go to what we did. Then here we're synthesizing phenol from benzene. So here I move to benzoic acid, not benzoic acid, benzene sulfonic acid. Then from benzene sulfonic acid, I can move to phenol via these reactions. So that is correct. And we have formed that product. Then another one was this. You guys can be taking screenshots. Another one was this. You realize that this also involves increase in the carbon chain. So when we are increasing carbon chain, we can use Grignard's reagent, and this we studied it under alcohols. Under alcohols. So this I actually converted this to a Grignard's reagent by adding PCl5 to form that. Then I add magnesium in the presence of dry ether to form now this is my Grignard's reagent that I'm going to add onto this to form this compound that I'm going to hydrolyze to form that compound. So you guys can snap that. You can take screenshots of that. Then here we're forming phenylethene. Phenylethene. So what I did the Friedel-Crafts acylation, forming that compound. Then I reduced it to form an alcohol. Then after me forming that alcohol, I dehydrogenated it. I dehydrated it, sorry. I dehydrated it to form an alkene. Then you look at this other one here. Aha. Now when you look at this one is actually the benzene, a benzene ring. Now whenever you're having two or more substituent groups. If I'm having two or more substituent groups on the benzene ring, last holiday I remember teaching it's important for us to know which groups are 2,4 directing and which groups are 3 directing. And we say the groups that have double bonds in them, are the ones that are 3 directing. Then the groups that have single bonds only, single bonds are the ones that are 2,4 directing. Now here in this case, we are forming this compound. So it's important for us to know which one are we starting with. Should we start with the nitro group or we start with the carboxyl group? You're seeing that. So what happens that you realize that this carboxyl group is actually contains double bonds. So when you open it up, it's like this. That is how it is when you open that up. So you realize that this carboxyl group is actually 2,4 directing. You're seeing that, meaning that if in case I am to nitrate, in case I'm to add a nitronium group onto it, it is going to allocate itself on position number 3. So it's important for us to know which one do we start with and which one are we adding and which position has been given in the question. So that is actually what I wanted us to note in this question number number 6. Then here, uh, here we're actually synthesizing this compound from benzene. We first form nitrobenzene. After us forming nitrobenzene, what happens is that we form a benzene diazonium salt. Now, after forming benzene diazonium salt, you react it with this compound in the presence of an alkali, and you get that compound. We looked at these under the coupling reactions of phenol. Under those coupling reactions of phenol. So I think that is done with that for today. So let's actually move to what we wanted to see today. Oh, some people were requesting me to go slow, but that's the work I just gave for revision. I want to start something new. Something new. And I'm actually going to, for those of you who have been attending my class, you realize that normally whenever I'm teaching organic chemistry, at the end of the week, I teach organic synthesis, because synthesizing organic compounds is an art that you have to learn. So this one, I was actually not teaching synthesis. I just want us to delve onto what has brought us here exactly, such that we can be able to do other things. So the moment I finish carbonyl compounds, I'm going to integrate a certain kind of, I'm going to integrate synthesis. In other words, how are you supposed to synthesize these compounds? Because in organic chemistry, you realize that you study a series of reactions. You're seeing that. Then you're going to use those reactions to apply them to actually synthesize compounds. That is actually what I wanted us to do. This guy of Infinix, the rules here is that we are not supposed to play with our screens. There is that pen-like structure which is on the left-hand side of your screen. Don't tamper with it. Just leave the screen the way it is. I don't know whether you guys are getting me. If we are free to proceed, please give me those Y's on the chat. If we are free to proceed, give me those Y's on the chat. So that is what we are going to do. At the end of the week, we are going to integrate very many aspects of synthesis, and I show you how they come about. But for today, I'm actually going to introduce carbonyl compounds. Now, for those of you who are in this platform is designed to keep you ahead of your classmates. So what we are going to do is that the whole of this holiday, we are going to study all the functional groups which are involved in organic chemistry. Then at the end of the holiday, I am going to publish for you the certain summary that I've written of organic chemistry that helps you to use all that information that you have been given to come up with solutions in organic chemistry. So let me start something new today. So today we are basically going to start looking at what we call carbonyl compounds. We are going to look at carbonyl compounds, and carbonyl compounds in itself is actually a functional group that we are going to study in organic chemistry. Now, what are carbonyl compounds? What are they? That is the first thing that will come to your mind. What are they? What are these carbonyl compounds? What are they? Now, carbonyl compounds are compounds that have a functional group. They have this as their functional group. They have that as their functional group. In other words, a carbon atom which is bonded to an oxygen atom. So this is serving as the functional group of these carbonyl carbonyl compounds. It's the functional group. And those of you who studied your senior 5 very well, you know that a functional group is the most reactive part of an organic compound. That is what I can tell you. Carbonyl compound, so long as you see a compound which is having this functional group, just group that compound as a carbonyl compound. Then we also have two classes of carbonyl compounds. We have two classes of these carbonyl compounds. The first class are called ketones. Ketones or ketones. Then the second class of these organic compounds are called they are called aldehydes. So there are two classes of carbonyl compounds. You can either have ketones or you can have aldehydes. Okay, in case you have anything to communicate, make sure you use the chat very well. In case you want to speak, you raise up your hand. I'll be in position to see it, and we continue. So there are two classes of these compounds, of these carbonyl compounds. We either have ketones and we have aldehydes. Now, what are ketones? What are ketones and how do they look like? So for ketones, you realize you actually have this. Ketones, most of the times you have the carbonyl functional group. Then you're having this R prime and R, where your R prime and R are actually alkyl groups. They're actually alkyl groups. So ketones actually are of that form. They have the carbonyl functional group. Then they are having alkyl groups that are attached to the carbonyl carbon. This is actually called the carbonyl carbon. It's called the carbonyl carbon. So in ketones, you're having alkyl groups being attached onto the carbonyl carbon. For example, you look at maybe I'm having CH3, C, double bond O, CH2, CH3. This one here is a ketone. Why? Because we are having alkyl groups, two alkyl groups attached onto the carbonyl carbon. This is one alkyl group, and this is another alkyl group. So that qualifies to be a ketone. You can also have something like this. You can have that. You can also have maybe CH3, C, double bond O, CH3. So this is also a ketone. Why? Because you're having your carbonyl carbon. My carbonyl carbon is there. Then I'm having two alkyl groups that are being attached onto that carbonyl carbon. That is how ketones look like. Then after ketones, you look at let's look at the aldehydes. Let's look at the aldehydes. Aldehydes, they also have this as their functional group. However, for aldehydes, we have one alkyl group. Instead of us having two alkyl groups, the other alkyl group is replaced by a hydrogen atom. You're seeing that? So this is one alkyl group. That is one alkyl group. Then this one here is actually a hydrogen atom. So for you to be able to distinguish a ketone from an aldehyde, you just look at this. For aldehydes, a hydrogen atom is directly attached onto the carbonyl carbon. A hydrogen atom is attached onto the carbonyl carbon. That is for for aldehydes. I think you guys understand what I'm trying to say. Then for ketones, you realize that the carbonyl carbon is having alkyl groups that are attached onto it. That is how ketones look like. So if I'm to give an example of an aldehyde, we can have CH3, CH2, R, double bond, H. I can have, that is one of the aldehydes. I can have CH3, C, double bond O, H. You're seeing that? So with aldehydes, most of the times, actually with aldehydes, all the time, a hydrogen atom is directly attached onto the carbonyl carbon. That is what we have special about these about those aldehydes. I think that is fine about the aldehydes. So when you look at these two, their difference in structure makes them also different via terms of reactivity. Their reactivity is different. Their reactivity is different just because of this small difference in their structure. So it makes them different, and it makes them, let me write it down. It makes them different, and it makes them to be able to be distinguishable. Distinguishable. So we can be able to distinguish between aldehydes and ketones. For those of you who have begun studying organic analysis, the practical bit of it, most of the times you can also be told to conduct tests to distinguish between aldehydes and the ketones. And we are going to look at that by the end of today. Not by the end of today, by the end of our holiday, we shall have looked at it. We shall have looked at that. I hope we are all fine up to now. Up to this point, are we all okay? For those of you who have been with us, you know how we do it here. You type for me those Y's on the chat. If you're okay with where we have reached so far, please give me those Y's on the chat. Aha. That is very nice to hear. Aha, give me those Y's on the chat. So I'm just pounds. Then the next subsequent weeks, we are going to do other functional groups. We have carbonyl compounds, we have amines. Now, last holiday, I looked at benzene, aromatic compounds, and alcohols. This holiday, I'm going to look at the remaining ones: carboxylic acids, carbonyl compounds, amines, then esters. There are 4 functional groups that are remaining. I think that is fine. It means that we can continue. So on continuing, the next thing, for those of you who have been here with us, I told people that in organic chemistry, there are about 4 things we focus on. One of them, we focus on the nomenclature of these organic compounds. In other words, how are we able to name these organic compounds? You're seeing that? Then we can focus on the reactions of these organic compounds. And in reactions, we shall look at the mechanisms of those reactions. So in organic chemistry, we are so much interested in analyzing the mechanism. In other words, how do these reactions proceed? Then we can also look at synthesis. So synthesis is also important in organic chemistry. In other words, how do we prepare these organic compounds? So preparation is also key. So whenever we are studying a functional group in organic chemistry, we delve so much on the nomenclature. How do we name carbonyl compounds? How do we name alcohols? How do we name carboxylic acids? How do we name alkenes? And this nomenclature is based on a certain kind of system that is called IUPAC. An IUPAC system. IUPAC in full is International Union of Pure and Applied Chemistry. This is a body that sits down to decide on why we call alcohol alcohol, but not any other name that you'd think about. You're seeing that? So that is it. So we actually name our organic compounds according to the IUPAC system. In other words, the IUPAC system is actually standard. Everybody all over the globe, if this is called propanol, everybody either in China, either in Finland will call that compound propanol. That is why we have IUPAC there. Instead of us having a system whereby Ugandans are calling this compound, in Tanzania it's different, in America it's different, something like that. So IUPAC actually has dealt with that. Then we look at the reactions, the mechanisms, then the synthesis, how we prepare those organic compounds. That is very, very key. Now, straight allow me delve into the nomenclature. So I want to delve into the nomenclature. So you can look at nomenclature. In other words, how do we name? And the naming is based on the IUPAC system, the International Union of Pure and Applied Chemistry. Obviously, by now, I expect some of you to be dreaming to work with IUPAC. At least in future, somebody should come to me like, Teacher Kenneth, I'm now working in IUPAC. We have actually decided to call these compounds this, and it's no longer what you taught us. We have actually changed it. I will actually be very proud to have you guys doing that. Now, whenever we are naming these organic compounds, by now you should be very familiar with the rules of nomenclature for our level. First and foremost, we have, for example, when you are naming, all the names are actually derived from, all the names are derived, they are derived from the alkanes. You're seeing that? For example, I'm having CH3, CH2, CH3. This compound here can be named as 3 carbon atoms, meaning it is prop. So this is propane. You're seeing that? But if I'm having a compound like this, CH3, C, double bond O, CH3. Now this compound is a ketone. You're seeing that? Now for ketones, what we are going to do, instead of us having the E for the alkane, we are going to replace it with a suffix that is, it's called on, or you can call it one or on, something like that. So this is composed of 3 carbon atoms. You're seeing that? And we cannot, and instead of us naming it propane, we are going to name it propanone. You realize that the E of the alkanes has actually been replaced with non. That is for ketones. Then for an aldehyde, for example, let me do the same aldehyde with 3 carbon atoms. One aldehyde, let's derive the name from an alkane. This one here would also still be propane. But instead of the E for aldehydes, we are going to replace it with Al. In other words, al or all. I don't know how you pronounce it. So this compound, we are going to call it propanal. So propanal shows that is an aldehyde. Then propanone shows that it is a ketone. That is the first rule for nomenclature. And this one here just goes for simple carbonyl compounds, the ones with less than 4 carbon atoms. For example, you have this HCOH. This one is having 1 carbon atom, and you realize it's actually an aldehyde. So this one is called methanal. Methanal. Or I can have CH3, CO, CH2, CH3. You're saying that this one is having how many carbon atoms? 1, 2, 3, 4. 4 carbon atoms. So I'll call this compound. I'll call this compound 4 carbon atoms. That is a bute. So this is it's butanol. Aha. So that is for simple, let me call it for simple carbonyl compounds. In other words, carbonyl compounds that have 4 carbon atoms and below, less than 4 carbon atoms. We can just name them like this. Then let me look at the second aspect. Then 2, if you're having one having more than 4 carbon atoms. If it's having more than 4 carbon atoms, meaning that you're supposed to specify the position of this functional group. To specify the position you're supposed to specify the position of the functional group. Why? Because within that compound, the functional group can be in position to be in very many positions at the same time. You're seeing that. So when you're naming a compound with more than 4 carbon atoms, you're supposed to be able to specify the position of the functional group. And then here we said, remember in our other alcohols and other functional group, we say that we give the functional group the least possible position. The least possible position. When we are counting from the left to the right or from the right to the left. That is what we do when we are specifying the position of the functional group. Let me give you an example. For example, I'm having this compound. This is EG. So you're having that compound as long as it is. You're seeing that. So you realize that with this compound, we have to specify the position of the functional group. Why? Because the functional group can as well be on that carbon atom, or it can be on this carbon atom. So that makes them different compounds. So we have to specify. So firstly, we check on the number of carbon atoms. So there are 1, 2, 3, 4, 5. So if it is 5, it qualifies to be a pent. So pent. Now, what is the position of our functional group? If I'm counting from the left to the right, the functional group is having position number 2. If I'm counting from the right to the left, the functional group is going to have position number what? 1, 2, 3, position number 4. And we said we give it the least possible position. So we are going to have pent what? Pent 2. Since it is a ketone, pent 2 what? We shall have pent 2 on. Like that. So we have specified the position of the functional group. And this one is actually common for ketones. Because aldehydes, obviously, if I'm having an aldehyde which is of that same number of carbon atoms, it will still be like this. CH3, CH2, 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 1, 2, 3, 4, C, double bond, H. So here we cannot, the functional group is still on position number 1. So this one can just be called pentanal. That is the compound. So those are the 2 basic rules we can use for nomenclature of this organic compounds. Then obviously there are other compounds. for example, the other compounds that have special names, for example, look at this one here. That is an aromatic aldehyde. This one's name is called benzaldehyde. That one is called benzaldehyde. Then there are others that have the benzene ring attached onto them. For example, you have you're seeing that? Now here in this case, we are actually going to name, we are going to be in position to name the benzene ring as a substituent group. And I remember last holiday I told you guys that when we are naming the benzene ring as a substituent group, we call it phenyl. Phenyl. So in this case, we are going to name this as phenyl. It's going to be phenyl. These are two carbon atoms, so it's going to be phenyl ethanol. So that is how we name those organic compounds. Unless somebody is having a serious question. Let me look at your charts. What confuses me is how do we differentiate a phenyl and a benzene? Now, most of the time, when I'm having how you differentiate a phenyl and a benzene. Now, some compounds that have the benzene ring bear special names. For example, I looked at that last term. That person could be a new person. For example, look at this. This one here has a special name, and its special name is called benzene sulfonic acid. Benzene sulfonic acid. This one is having a special name. I cannot say phenyl sulfonic acid. You're seeing that? Then you have, you can also have this. You can also have this. OH. This one here has a special name. We can call it phenol. You're seeing that? But whenever the reason why we can call the benzene ring phenyl is when the benzene ring is bearing another functional group. Let me write that in red. Most of the times we call it phenyl when the benzene ring is bearing another functional group. When the benzene ring bears another functional when it bears another functional group. For example, let's look at this. In this case, the benzene ring is actually bearing a functional group that is actually attached to a compound which is having another functional group. So in this case, you're not going to call it benzene, you're going to call it phenyl. Why? Because benzene in this case is actually acting like a substituent group. It's acting like a group that has been attached onto that compound. The same way we can say that this is methyl, maybe methyl propanol, like that. It is actually acting like a substituent group. It is not the picture. It's not the main, how do I call it? The benzene ring is not the focus of that compound. When you look at this compound, the focus of that compound is the carbonyl functional group. So we call that phenylethanol. That is how we can call that compound. So that is how we do, that is simply how we can do nomenclature on these carbonyl compounds. Anybody with a question? Then why do we have benzoic acid? Still that one falls under special names. We can have aminobenzene. You're seeing that we're having benzoic acid, nitrobenzene. You're seeing that one falls under special compounds. Now that benzoic acid can also be called benzene carboxylic acid. So you just be able you should be in position to know the ones that have special names, then you'll be able to integrate with the others. With time, you realize that will become easier. Then there are some things that your brain will also refuse. When you're trying to do something, there are certain things that your brain will refuse. There's a certain nomenclature, a name you will name your compound, and even your brain will tell you that this one here, no way, it is not possible. So if you're okay, if you're good for us to proceed, we can proceed. Today I'm just doing introduction, and trust me, last holiday in 2 weeks, we covered 2 functional groups. In other words, we looked at benzene, then we looked at benzene, then we looked at alcohols and phenol. That work was done in 2 weeks. Now in this holiday, in this 1 month, and the next January 1 month, or about 3 weeks of January, we are going to cover the entire syllabus of organic chemistry and chemistry at large. So make sure you don't miss out. Make sure you don't miss out. Use this entire week to convince yourself that you're in position to attend the entire holiday program without fail. I hope that is fine. How many guys are willing to join us? If you're willing to join us, type for me a K on the chat. If you're willing to join us, please don't miss out. This is actually something which is not common. You're going to have the entire holiday covered, including biology. Next week, I'm going to look at serious topics like evolution. Now you see, when you see evolution, when a teacher begins teaching it, if you're not really stable, you can even take a full year to understand it. But we are going to look at topics like evolution. We are going to look at coordination. We are going to look at inheritance. Inheritance, that is genetics. We are going to look at very, very, very serious topics. So make sure that you're going to be a part of this movement. Now, for those of you who, what about physics and math? I only do biology and chemistry. Mathematics is a simple game. You don't even need to attend an online lesson for it. Anyway, but you can actually do the mathematics easily. But the biggest core is biology and chemistry. Okay, so I think we can proceed. So encourage your friends. I'm actually going to send links after this lesson for you to join our WhatsApp groups. Now this girl here, you guys, I told you guys don't play around with your screens. All the branches of chemistry, yes. This holiday I'm actually planning, in inorganic, I'm planning to cover what we call the transition methods. That is actually not the biggest, but the most challenging part of inorganic chemistry. When you finish that, it is going to be very easy for you to handle the rest of the inorganic chemistry. Last holiday, I handled physical equilibrium. For those of you who were not there, and the ones who were there can testify, they have enjoyed it. I'm very sure. Okay, now we are going to look at the next aspect. We are going to look at the next aspect on that. The next aspect we are going to look at is obviously the physical properties of these compounds. You guys, now friends, please excuse me. You guys who are playing around with your screens, please let's not we are mature people, and by now I expect you to exercise at a level of decorum when you're doing your things. Let's not over make this a game. Because those of you who are making those funny marks, you're really spoiling the entire thing for others. So let's have some decorum, man, and see what happens. Now, the next thing I'm going to look at is the physical properties. I'm now going to look at the physical properties. I'm sure you guys are going to enjoy physical chemistry. By the time you're going, and then now the beauty about organic chemistry is that when you finish studying all the functional groups, we shall spend time, even if it is a week, and we can do a lot of numbers on synthesis and all that, and you realize how easy it's going to become. Now let's look at the physical properties. Physical properties of these compounds. What are the physical properties of these compounds? We can start with solubility. Solubility. Now, when it comes to solubility, you look at these compounds that have a low molecular mass. The carbonyl compounds, in other words, lower, let me call them lower carbonyl compounds actually they are soluble. They are soluble, or they are miscible. They are miscible with water. So lower carbonyl compounds, I mean carbonyl compounds that have a small number of carbon atoms. For example, you can say methanol. Methanol, that's an aldehyde. You have ethanol. You have ethanol. All those are. Do we have ethanol really? No, we don't have ethanol. We have propanol. Propanol. Now, all these lower carbonyl compounds, are actually soluble in water. You're seeing that? And then the higher ones, the higher carbonyl compounds, higher carbonyl compounds are insoluble. In water. So what happens is that solubility decreases with increase in the bulkiness of the hydrocarbon tail. It decreases with increase in the bulk of the hydrocarbon chain. Hydrocarbon chain. So the longer, the more bulky the hydrocarbon chain. For example, I'm having CH3, CH2, 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 maybe CO, CH3, CH2. You see that these carbon chains are actually bulky. You're seeing that. And that bulkiness is actually going to make the compound less soluble in in water. The reason is because that this hydrocarbon part of it is actually, they're actually hydrophobic. Hydrophobic. Glory, please stop playing around with our screen. This hydrocarbon part of it is actually hydrophobic. So as the hydrocarbon chain keeps on increasing, so does the solubility in water keep on decreasing in that format. That is one of the properties about that. Then you look at let's look at the boiling point, the boiling and melting points. The second physical property is the boiling and melting points. What can we say about their boiling and melting points? The boiling and the melting points of these compounds. The first thing that we'd recognize is that in comparison to alkanes, these carbonyl compounds, the carbonyl compounds have higher carbonyl compounds have higher melting or boiling. They have higher melting or boiling points. And the question is why? So for example, we are comparing maybe CH3CO, CH3. Then I'm going to compare it with CH3, CH2, CH2. Now this compound is what? Propanol. Then this is propane. So they can give you data and they can tell maybe this one here has a boiling point of maybe 121 degrees centigrade. This one has a boiling point of maybe let me assume it is 97 degrees centigrade. And you can be told to explain that result. Propanol is having a higher melting or boiling point compared to propane. And the reason we have for that is that first and foremost, when you look at this CO, the carbonyl functional group, when you look at that carbonyl functional group, you realize that the oxygen atom here is actually more electronegative. It's more electronegative compared to the carbon atom. And what is electronegativity, by the way? Electronegativity refers to the tendency of an atom to draw a bonding pair of electron more towards itself. So these bonds here between carbon and oxygen are composed of electrons. So what oxygen does is that because it is more electronegative than carbon, it tends to pull the bonding pair of electrons more towards itself. Thus, it acquires a partial what? A partial negative charge. Then this carbon atom acquires a partial positive charge. For that reason, the carbon-oxygen bond is going to be polar. You're seeing that? The carbon-oxygen bond is going to be polar. And because the carbon-oxygen bond is polar, there's a particular kind of forces of attraction that we are going to have among these carbonyl compounds. And these forces of attraction are called permanent dipole van der Waals forces. Van der Waals forces. So those molecules are actually going to associate by these permanent dipole van der Waals forces of attraction, which are actually strong and require a lot of energy to be overcome at at a particular temperature. Meanwhile, for propane, the molecules are held by temporary. Instead of permanent, they are temporary. In other words, they are held by, we can just say, by weak van der Waals forces of attraction. They are held by weak van der Waals forces of attraction, and that makes their boiling point low. So in comparison to alkanes of a comparable molecular mass, carbonyl compounds have a higher melting or boiling point. Why? Because the carbon oxygen bond in carbonyl compounds is actually polar, making the molecules associate by permanent dipole van der Waals forces of attraction, which are actually stronger than the forces of attraction, the weak van der Waals forces of attraction in alkanes of a comparable relative molecular mass. I hope I'm well understood there. Friends, are we understood there? Are we repeating all the topics that you taught when we were not there? I'm going to revise those topics. That is what I'm going to do. Are we fine? A consultant is very happy, almost 10 wise. Okay? Pardon the reason I said that in carbonyl compounds, that functional group, the CO functional group, we say that oxygen is more electronegative than carbon. You're seeing that? In other words, electronegativity refers to the ability of an atom to draw bonding pairs of electrons more towards itself. Now, oxygen is going to draw those bonding pairs of electrons more towards itself, causing it to have what? Causing it to actually acquire a partial negative charge, as carbon acquires a partial positive charge. Because of that, the carbon-oxygen bond is going to be polar, making carbonyl compounds be held by a stronger kind of force known as the permanent dipole van der Waals forces of attraction, which are stronger than the weak van der Waals forces of attraction that hold the alkane molecules together. Are we fine? Then, I think we are fine with that. You guys are actually very okay with that. Okay, even Esther is fine. Esther. These names are actually common. These are guys who have been with us from first term's holiday in senior 5. So you guys, thank you for being consistent. Okay? Then we are also now we are comparing the melting and boiling point of these carbonyl compounds compared to alkanes. But this time, is it 2 or 3? Let me look at that. This is 3. So compared to alcohols and carboxylic acids. So if we are to compare, Pascal is raising up his hand. Pascal, you can unmute and ask if you have something to say. Pascal, you're raising up your hand. I've allowed you to unmute.
Oh, yes. Can you hear me?
I'm hearing you.
Tisha, I was actually disturbed a bit. I don't know whether it is my network or yours. I don't know if you can just repeat a bit that last step.
Actually, what is going to happen is that the recording is going to be availed. So don't mind. Because I've repeated that step over 6 times. But the recording, you're going to actually get the recording and you can go over it again and again. I think that is fine. I think we are fine to move on. So in this case, we are comparing it to alcohol and carboxylic acids. So how does the melting and boiling point compare? So let's look at alcohols. Alcohols, you realize alcohols have this hydroxyl functional group. Then carboxylic acids have a carboxylate functional group, which is like this. You're seeing that? That is for the carboxylic acids. This is for the alcohols. You're seeing that? Now for it means now when you look at this, you realize that still you're having oxygen and hydrogen, meaning that oxygen obviously being more electronegative than hydrogen makes it to acquire a partial negative. This acquires a partial positive. Partial negative, this is a partial positive. At the end of the day, these alcohols, the molecules of alcohols and the carboxylic acid, they associate by stronger hydrogen bonds. These hydrogen bonds are strong and they cannot be easily overcome at a particular temperature, compared to these other carbonyl compounds that do not associate by hydrogen bonding. We talked about alcohols. We say that in alcohols and carboxylic acids, their molecules associate by stronger hydrogen bonds, and because they associate by strong hydrogen bonds, it makes them what? They cannot be easily broken at a particular temperature, and that gives them a higher melting and boiling point compared to carbonyl compounds. I think we are fine with that. I hope we are fine with that. I hope we are fine with that. So for those of you who have not yet subscribed for the holiday, make sure you do so, because we are going to have a blast this holiday. By the time you're getting back to school, people will be wondering, where are you from? You'll be smelling different from your other classmates. Trust me, the guys who have been here know it. You ask guys like girls like Promise. Promise has been with us from first term halls, and I'm sure she smells differently from other people. Okay? So make sure you subscribe by the end of this week. How do you subscribe? If you're on our WhatsApp platforms, all the messages are there. All the information you need is actually there. You just have to be able to deposit your money on my line. You give me a call, then I send you the links that you need for the holiday. So your work will just be to tap on it when it is time for the lesson, and you'll be okay. Somebody, I think, asked a question. Let me first check on your chat. Are the lessons held every day? Yes, the lessons. Now, these guys who don't have information, make sure you join our WhatsApp groups. You can inbox me and make sure I add you, because all that information is there. Even the timetable is there. Every day at 8:30 we shall be here. Where can we find the recording? In our WhatsApp groups, everything shall be there. Where can we find the recording? You find it on the WhatsApp group. About the subscription. Now, if you're in our WhatsApp groups, the only thing you need to do is to make sure you, let me just give out my phone contact, 0778 695,681. This is teacher Ken. So you can take that contact. You can take that contact. Yeah, you guys will smell different. How do we subscribe? My contact is on the screen. You can just call me anytime and I'll tell you. Guys who are not in the group, make sure you take my contact, then you inbox me on WhatsApp and I add you. Or do Emmanuel, my contact is there. Make sure you take it and I will add you. You're supposed to do it within this week because this week the lessons are free. So you're supposed to do it within this week. My contact is on the screen. For more information, just call me. Explain why aldehydes are more reactive than ketones. How can you join the WhatsApp groups? My number is there. Okay. So let's delve into the other aspect. Now I'm going to explain why aldehydes are more reactive than ketones when we are looking at the reactions of carbonyl compounds. So when we are looking at the reactions of carbonyl compounds, we realize that carbonyl compounds undergo what we call nucleophilic addition reactions. You're seeing that. So I'm going to explain to you why aldehydes are more reactive than ketones when we reach that aspect. Then the final aspect that we have to look at tonight, the final aspect we are going to look at tonight is now going to be the laboratory preparation of the carbonyl compounds. I think I've reached the target for today. So here is laboratory. Is that the spelling of laboratory? Looks like I'm writing in local language. Let me first check on it's laboratory. Preparation. So how do we prepare carbonyl compounds within the laboratory? That is actually what I'm going to look at. Then we call it a night well spent. The way we prepare carbonyl compounds in the laboratory, one of them is by oxidation of alcohols. By now, we should be able to know that we have two classes of alcohols. Class A is the primary alcohols. The second class is the secondary alcohols. Now, the primary alcohols, the oxidation of primary alcohols leads to the formation of the oxidation of these primary alcohols leads to the formation of aldehydes. Then the oxidation of secondary alcohols leads to the formation of ketones. However, there is a note here on these primary alcohols. When we are oxidizing primary alcohols, it is called controlled oxidation. The oxidation is controlled. How is it controlled? By using a weak oxidizing agent. We use a weak oxidizing agent. Why? Because when you use a strong oxidizing agent to oxidize primary alcohols, you end up having a carboxylic acid. You're seeing that? So for this, we actually do a controlled oxidation of primary alcohols to yield aldehydes. Then for secondary alcohols, you can use strong oxidizing agents. They will all work. For example, for primary alcohols, I'm having a CH3, CH2, OH. So I can use a weak oxidizing agent can be manganese 4 oxide in the presence of an acid, then I heat. Or another oxidizing agent, you can have chromium, chromium 6 oxide in the presence of an acid, then you heat. And any other weak oxidizing agent that you know. This is going to give us an aldehyde. That is giving us an aldehyde. Then, for secondary alcohols, yields for us ketones. Secondary alcohols yield ketones. For example, I'm having CH3, C, OH, H, CH3. So here, if I'm to use, now here we can use a strong oxidizing agent. For example, potassium permanganate in the presence of an acid. In the presence of an acid, then we heat. This is going to yield for us a ketone. It's going to yield for us a ketone. So that is the first way we can prepare carbonyl compounds, by controlled oxidation of primary alcohols using a weak oxidizing agent yields for us aldehydes. Then using for secondary alcohols, oxidizing them leads to formation of a ketone. That is the first thing I wanted us to look at. The first thing I wanted us to look at, let me look at your charts. Monohydric alcohols. Monohydric alcohols are actually alcohols that have one hydroxyl. They have one hydroxyl group. So we're looking at monohydric alcohols, in other words. How can I differentiate between secondary and primary alcohols? We looked at that under alcohols, but I'm actually going to revise all that work. What about tertiary alcohols? Tertiary alcohols cannot be oxidized. That is one note you should put there. Tertiary alcohols cannot be oxidized. Tertiary alcohols cannot be oxidized. Now what I want us to do is that I want to take screenshots. Take screenshots of the work, because we are ending the lesson now. What we have covered is enough for now. The recording is going to be availed in the group. By tomorrow's morning, it will be ready. So take screenshots of that work. Take screenshots of that work, and please post those screenshots and share them with your friends, such that they be able to see what we are doing. Melting and boiling points. My phone number is there, guys. Those of you guys who are not who don't have it, you can take it. You can take that. But still, I'm going to share this PDF in the group. Okay, I think we can end today's lesson here. My machine is actually going down. My machine is going down. Let's end there for today. let's end there for today's lesson, and we shall actually continue from there the next time we are meeting for organic chemistry. Thank you for attending. Encourage your friends to attend. Those of you who have not made your payments for week 1, the lessons are every evening. Tomorrow we have biology. So let's share the information with our friends so that they're in position to join us. Thank you for attending, and I wish you the best. The recording is going to be available by tomorrow's morning. I wish you guys the best. We shall actually meet tomorrow. Tomorrow for biology. The following day we shall meet for chemistry. Like that. Until this week gets done. Inform your friends to join us so that by the time we are starting next week, we won't leave anybody behind. What of physics? Apparently, I don't know anybody who is teaching physics online. I would recommend, but I don't know. All right, guys, thank you for attending. Spread the gospel to your other friends. Tell them to be able to join us.